good afternoon, evening, morning, and whatever time continent you're on at the moment. So welcome to this webinar. My name is June Freeland, and I'm the chair of the ABSANZ Education and Training Committee. For those of you who may not know, ABSANZ is a peak professional body for Australia and New Zealand in the biosafety and biosecurity sector. And the purpose of ABSANZ is to protect people, the community and the environment through the advancement of knowledge in biosafety and biorisk management. So if you look at my background, there's a bit of advertising going on behind me. This is for our face-to-face conference in November, addressing the topic of biosafety at the crossroads, which is very topical at the moment, and just where do we go from here? So before we start, a few digital housekeeping rules. I hope you've all found the question and answer button. So please use this to ask your questions and not the chat function. Our presenters will endeavour to answer them throughout the presentation, but any remaining questions will be collated at the end and I shall ask the presenters on your behalf, time permitting, of course. So I'm delighted at the collaborative event we're about to have with the Australian Institute of Occupational Hygiene, and I really look forward to more of these in the future. So now I'd like to introduce and welcome our presenters today, Kate Cole and Dr. Julia Norris of the AIOH. I hope you've had a chance to read their biographies. They're extremely impressive. Just very briefly, Kate is the chair-elect of the AIOH and is a practicing occupational hygienist. And Dr. Julia Norris is also an occupational hygienist and a medical general practitioner. So I'm not going to steal any more of your time, ladies, and without any further ado, I'm now going to hand over to you both. Thank you.
Well, thank you very much. And it's an absolute delight to do webinars where we collaborate with other agencies. So on behalf of Julia and myself, a big thank you and welcome to everyone that's joined today from either association. So I'm going to run the first half and then I'm going to handball over to Julia. And because this is a collaborative presentation, I thought I'd start with the basics for those that may not know what occupational hygiene is or what occupational hygienists do. Look, we're basically scientists and engineers. We focus on worker health protection. We have a really broad understanding of the many interventions that are necessary to protect the health of those in different sectors from a wide variety of hazards. And in the context of COVID-19, typically occupational hygienists have a really good understanding of infection control, epidemiology, toxicology, aerosol physics, ventilation, respiratory protection and PPE, human factors and workplace health and safety more broadly. So it's always useful to have an occupational hygienist in your pocket, I say. An outline of what we're going to go through today, I'm going to talk about aerosols, what they are and how they move. I'm going to take you through source control and pathway control. And then Julia is going to go through receptor control. But first off, I'll start with the basics about, well, what are aerosols? Look, airborne contaminants occur in the gaseous form, so gas and vapors, or as aerosols. And aerosols can be in the form of airborne dusts or sprays or mists or smokes or fumes. And in the occupational setting, all of these are really important because they relate to a really wide variety of occupational diseases. As occupational hygienists, we spend a lot of time in managing risks associated with aerosols of various types. And of late, most of that has been related to biological aerosols containing SARS-CoV-2. But when it comes to aerosols, there's two main factors that we look at as occupational hygienists to help us understand the risk that they might pose. So the first is the composition of the aerosol and the second is the particle size. Composition is really important because it helps us understand its toxicity. So if, for example, it represents or presents an acute health hazard like pollen, or if it's a chronic health hazard like crystalline silica that might cause silicosis, for example. The second factor is particle size. And this is important because it determines how long an aerosol remains airborne and how far an aerosol cloud can disperse in a workplace before it soars. And this really affects the choice and impacts the effectiveness of control strategies put in place to protect people in the workplace. Understanding particle size also helps us better understand the health effects caused by the site of that'll be deposited in the respiratory tract, for example. So large particles settle in the nose and the throat, and very small particles, which we term respirable, can settle into the gas exchange region of the lung. And I've just shown on the screen some of the wide variety of aerosols that we deal with as occupational hygienists. And you can see at the bottom in the lighter shading, that's typically the biological aerosols that we deal with as well. So just some basics. Here's the effect of particle size on the behavior of aerosols. So if we're dealing with really large particles, like greater than 100 micron, we know that those particles will settle out of the air relatively quickly. Maybe a good analogy to use is beach sand. You throw it up and you see it falls down really quickly. But if we're dealing with particles or aerosols that are at the smaller end of the spectrum, say around 5.5 micron, that's a bit more like cigarette smoke. If we're dealing with particles around that size, then we know we need to increase our control measures on airborne controls to prevent exposure, because those aerosols are going to stay suspended in air for a significant period of time. Look, in the context of occupational health and aerosols, we know that all particle sizes shown on the screen here, so up to 100 micron, can be breathed in. So all of these sizes are airborne. So we put strategies in place to prevent inhalation from all of these particle sizes. Similar to chemical hazards, biological hazards can come in a range of sizes. Some are really large, like in the case of this sneeze shown here, which can be bigger than 100 micron. And some of them are smaller, such as those that we emit when we breathe, and they can be smaller than 1 micron. But you see, biological aerosols are really tricky. Different people can emit different sizes. And you can emit more when you sing louder in comparison to singing softly. There's no exact cutoff when they become a problem. You can't tell a person to emit less aerosols, or I guess you can tell them, but they're not necessarily going to do it. It's hard to stop people shouting or talking or running or exercising or coughing or breathing. Humans are very unpredictable. That's what makes biological aerosols so incredibly interesting and fascinating. But it's important to understand that there is a continuum. And if someone emits really large aerosols near you, like a sneeze, for example, they're also going to emit fine aerosols as well. It's not one or the other. It's quite a big mixture. So coming back to SARS-CoV-2 specifically, it's important to remember how the virus travels, which is through aerosols. The virus, not shown to scale here, doesn't move naked in air. It's not just out there by itself. While the size of the virus is 1 micron or so, that's going to be in aerosols that might be up to 100 micron or smaller than 0.5 micron, which is why as occupational hygienists, we focus our control of transmission strategies on this high range of aerosol sizes. So it's not just big droplets, but it's all sizes of aerosols. So the distinction between the size of particles comprising an aerosol and the size of particles that settle out quickly is really important. Spherical particles settling freely in air will reach an equilibrium or a terminal settling velocity, and this can be calculated. The terminal settling velocity of particles can be used to distinguish those that tend to remain airborne from those that settle out. But I guess what's challenging is that aerosols don't necessarily remain the same size after they're expelled by people, but they can begin to immediately evaporate and within seconds or even fractions of a second become smaller aerosols. Again, this is what makes biological aerosols so complex and inherently interesting. But all aerosols within that sort of continuum of size are going to move to wherever that it takes them. And that's why airflow is so incredibly important, and probably having a good understanding of the fact that aerosols are generated, they will accumulate in enclosed spaces, and they can be carried or dispersed by ventilation is a really key message with all of this. So on to source, pathway, and receptor. So infectious diseases can be transmitted in a number of ways, and key to preventing disease spread is to focus control strategies in the 3 areas of source, pathway, or receptor. Another way of looking at this is the chain of infection model, which is used in healthcare. It follows the same approach through looking at the source of the infectious agent, the pathway being the mode of transmission, and the receptor being the susceptible host. Key to breaking this chain is to implement control strategies that focus on each one of these 3 areas, which is what we're going to go through today. So when we're designing strategies to prevent or minimize exposure, we refer to the hierarchy of controls as our guiding principles. It's a step-by-step approach to eliminating or reducing risks, and it ranks control measures from those of highest level of protection and reliability to those that are a bit lower. So eliminating the hazard is always our first step, followed by reducing the risk through substitution and engineering controls, then administrative controls, and lastly, through the use of personal protective equipment. And we apply this hierarchy to each of the steps. So on the source, on the pathway, and also their receptor. So as you go down the hierarchy, the effectiveness of these control measures decreases. And that's because things like organizational policies or training or instruction or mask wearing rely on human behavior to be effective. The most effective control is to remove the source. And we can do this in non-essential workplaces, but of course this can't be done in workplaces like hotel quarantine or healthcare. And it's for this reason that the use of mask wearing as source control is so incredibly important. And I'm talking about return travelers and patients here, not the workers themselves who need higher grade protection, such as respiratory protective equipment, for example. So masks, including surgical masks, are intended to protect others from substances expelled by the wearer, versus respirators that are designed to protect the wearer from aerosols in the work environment. There's a very distinct and important difference, and I won't steal Julia's thunder talking about respirators now, because she'll talk about them a little bit later on in this presentation. I wanted to share this video because I think it's a really good visual about the effectiveness of using masks or no masks during common practices of speaking and sneezing. And you can see it really clearly here. A lot of work has been done in this space by many people around Australia and internationally. This video is courtesy of Professor Rana McIntyre. If you're not familiar with her work, I very much encourage you to read it. So if we go to pathway control, again, as you go down the hierarchy, the effectiveness of these control measures decreases. So today I'm going to focus on the high level, which is ventilation. And when it comes to ventilation as a control measure for SARS-CoV-2, there's a few key areas that I guess I want to draw your attention to that we would look at as occupational hygienists. We would first look to maximize outdoor air into indoor spaces. We would look at ways to remove virus-laden or contaminated air out of a space and replace it with clean air. We would look to avoid the buildup of contaminated air and ensure appropriate dilution of ventilation. We would look to increase ventilation rates where it's practicable to do so, understanding there's lots of constraints around that in already constructed buildings. We'd seek to really understand and control the airflow to meet the environment or the situation that we're faced with. And then we would seek to really understand if what's on paper is what's actually happening in the field. Because as hygienists will know, just because it's written down in a procedure doesn't necessarily mean that that's what happens when you actually get to the workplace. And ventilation is no exception. We need to make sure that we're auditing and understanding what's really going on. There's lots of examples of approaches to ensure good indoor ventilation, but the devil's really in the details in understanding what you're trying to achieve in your particular scenario. So here's one example of an approach from the WHO for mechanical ventilation in high-risk workplaces like healthcare and managed quarantine, which we happen to do in hotels. So the first challenge with implementing this in Australia, that we use hotels for quarantine, and if we follow this roadmap, the WHO actually wants us to have really high airflow of around 60 litres per second per patient, or around 6 air changes per hour. But in hotel environments, they're not designed that way. So there's only about 10 litres per second per person of fresh air, and the air change rate might only be around 1 to 3. So that's far lower. So we're already starting at a really low base. But this is a roadmap, so it helps us understand what we can do. And if we follow the WHO recommended strategies, if the ventilation rate can't be met, then this roadmap recommends that ventilation is maximised by using natural ventilation, by opening windows. And that can be a really big problem in hotel quarantine, and it highlights just one of the many challenges in writing overarching guidance on ventilation for different types of scenarios. But I'm going to use hotel quarantine as just one example of a high-risk workplace where ventilation as a pathway control is incredibly crucial. And I'm going to start with pressure. So hotel ventilation rates are not designed to be that of a hospital system, that's a given. So what will happen is that aerosols will build up inside that space, inside the hotel room. And if a guest room containing a return traveller is under positive pressure, it means that the contaminated aerosols within that room will move out of the guest room. And they'll do this through gaps in the door, or mostly under the door where there's the biggest gap. And in Western Australia, the publicly available report on hotel quarantine reported that some of the hotels were pushing out around 40 litres a second or more continuously from guest rooms actually into the corridor. Now, this is a problem because corridors in hotels are typically poorly ventilated, and they don't necessarily always have dedicated ventilation systems, which means that contaminated air doesn't get diluted quickly and aerosols again build up in those corridor spaces. Workers who access those corridors, like security guards or cleaners or service delivery, are therefore at a greater risk of infection because the control measure to stop the chain of transmission or the pathway aren't effective. They're even at higher risk if they don't have receptor controls in place. So if they're not wearing respirators and they're only given surgical masks, for example. The creation of a negative pressure environment can be done within a hotel room through adjusting the HVAC system. However, maintaining the state continuously can be quite challenging because hotels are a dynamic environment. But it's typically done by increasing the rate of the exhaust fan, so commonly found in the bathroom, and ensuring that that is greater than the supply of the air coming into the room. The other issue in hotel quarantine is that contaminated air can move between rooms depending on how the HVAC system is balanced. Oops, sorry, that's my phone. Factors that will likely contribute to a higher dose, lower ventilation rates in the corridor, proximity to a high positive pressured room, being in the relief air pathway, a symptomatic guest that might produce aerosols at a much higher rate than someone else because humans are unpredictable, opening door times, etc., etc. It can be incredibly complex. Now, I've got a really basic example of what is kind of a complex issue. Let's just say that you have a negative pressure room inside hotel quarantine. And I spoke about the fact earlier that the WHO guideline recommends that you increase natural ventilation through windows. But let's assume that that negative pressure room at this point has a window. When you open the window, pressure is applied to that room, and then high pressure then moves to a low pressure. So openable windows or balconies then force that room to become positive sometimes, and then the air will actually move outside of that room. And that's why the use of openable windows or doors in guest rooms can be so incredibly, I guess, fraught with danger within hotel quarantine. So what happens if you have positive pressure rooms on one side of the corridor and negative on the other? Well, as you can imagine, it's a prime setup for airborne transmission of COVID-19 for sure. So I'd like to use this animation to show the effect of open doors or windows. This is a horizontal view of a room. And I think it's great because it shows what happens when the hotel, the guest room door opens. Air from the outside displaces the room air, and you can see that displaced air moves into the corridor. Sorry. Oh. And now I'm going to hopefully find a way to share my volume. So we know that aerosols can move outside of a hotel room and into a corridor, but what happens when the contaminated air in the corridor, where does it actually go? Does it stay in the corridor or can it go in another room? I'm going to share a little skit, this is my claim to fame, on 7:30, where I tried to reenact this particular situation. So hopefully you can hear this.
As an occupational hygienist, Kate Cole argues if ventilation inside the hotel had been properly reviewed, airborne transmission would have never occurred in the first place.
So when we open the door, we see that smoke escapes, just like aerosols and airborne transmission. It'll come into a corridor, it will sit there and it'll accumulate. And then when we go to open another door, that air will mix and go into that space as well. So now you know that it can actually go from one room into the other just from opening the door. And I will say that typically pressures in a hotel quarantine environment, even though they're negative pressure, or that's the aim in some states, not all unfortunately, the negative pressure may only be around 3 to 5 pascals. That's actually not very high. As occupational hygienists, if we're looking at positive pressure, heavy plant cabins in mining or construction or tunneling, we're typically looking at about 50 pascals, like really, really high. So it really doesn't take much just opening the door to actually lose that steady state and that pressure and enable aerosols to move within the room and the corridor. Now, I know I'm in transmission control and I skipped source control, but I actually think explaining this next section works best after going through what we've already discussed. Apart from the use of masks as source control, the use of portable air cleaners or HEPA filtration devices are also a really effective source control measure in this context. So let's take this incredibly simplified fictitious example that I've drawn up in hotel quarantine, which is 10 rooms, 5 on either side of a really long corridor, which has an exhaust fan at the end. So if a quarantining guest is infectious and they open the door in this end room, then some of those aerosols will move down the corridor. Pathway controls such as increased or dedicated ventilation in the corridor goes a long way to reducing transmission, but a better control is to put further controls in place at the source. So if you had portable air cleaners, you would reduce the contaminant burden within each room such that when the door is opened, the concentration of aerosols is further reduced. A significant amount of work has been done in this space by many occupational hygienists and mechanical engineers, one such being Professor Jason Monti, for example. I encourage you to read up on his work for further detail. I will say though that portable air cleaners have direct application outside of hotel quarantine. They also have fantastic application in places like schools or anywhere else where people congregate. So some basic principles, I guess, for ventilation in this context relate to these 4 key areas. I've tried to summarize a very complex element into 4 key items. The first is around airflow and rebalancing or adjusting HVAC systems to control that airflow direction to facilitate the movement of it from a clean to a contaminated area and ensuring that the airflow, we avoid recirculation. The second is an increased ventilation rate and maximising the outdoor air exchange rate as far as practicable to do so. and supplementing with localised HEPA air cleaning devices where we can to further reduce the risk. The next is filtration. So increasing particle filtration without impairing system function, because a lot of these buildings have been built for some time and the HVAC system is designed to withhold or have filters of a certain standard already. And the last is around servicing and auditing, to regularly service and check the system that it's operating as intended. And I guess two sort of red marks or things to watch out for is that in the context that I'm talking about today, quarantine, opening windows and doors can increase the volume of fresh air into outdoor spaces, but conversely, it can also increase room pressure, which can promote the spread of potentially infectious aerosols into adjacent rooms or hallways, and that can potentially expose others. And lastly, really, every building is unique. Every workplace is unique. And so if there was ever a situation that lended itself to individual assessments by independent qualified experts, it's absolutely ventilation and airborne transmission strategies to control that. And the best way to do that is to engage an independent expert. There's lots of occupational hygienists that have been engaged to support hotel quarantine and other high-risk workplaces such as healthcare that have been doing these very things. So now I'm going to pass over to my co-host, Julia, who's going to take control of the slides. And Julia is going to talk to you about receptor control.
Great. Thanks so much, Kate. And welcome everyone. So Kate has introduced the concept of source, pathway and receptor control. And my brief in the next sort of 20 or so minutes is to really talk and focus on receptor control. Obviously, looking at the hierarchy of control, which Kate's also introduced, there are higher order strategies around receptor control, but you know, vaccination being a really important one, but clearly that is a massive topic and not something that I'm going to go into detail about today. What I really want to focus on is respiratory protection. So while PPE, including respiratory protection, is considered the least effective and the lowest rung on the hierarchy of control, we do tend to rely on PPE as an interim measure. A lot of higher order controls take a lot of time to implement. And so we do rely on personal protective equipment and respiratory protective equipment as an interim control, and it is often the last line of defence. So where we cannot eliminate the hazard and there is still a risk, we do rely on personal protective equipment. So it's really important that we understand how to use it and that we get the most out of it. There we go. So while personal protective equipment is ranked as the least effective on the hierarchy of control, it is a really important way to protect a receptor from infectious aerosols. But the reason it's not on the lowest rung of the hierarchy of controls because it doesn't work. It absolutely will work, but it relies, as Kate said previously, on human behaviour, on adequate training and on supervision. So, you know, there's a lot of ifs and buts when it comes to the effectiveness of personal protective equipment and specifically respiratory protective equipment. We need to make sure we get the right respirator for the job. We need to make sure it fits correctly. We need to make sure it's used at all times when workers are in the hazardous environment. And we need to make sure that it's maintained and supplied correctly. So there's a lot of things that contribute to the effectiveness of personal protective equipment, which is why it's down there at the bottom of the hierarchy of control. But as I said, we do rely on it as our last line of defence. So I'm hoping I can provide a little clarity about this moving forward. I've already seen some interesting questions online around face masks and use of respirators with exhalation valves. And if there's still some remaining questions at the end of this, then we'll come back and talk about that. But as we're talking about respirators specifically as a receptor control, I'm just going to revisit this slide that Kate presented earlier. So what I'm talking about here is receptor control for the airborne transmission of SARS-CoV-2. And I'm talking about respiratory protective equipment. So just to be very, very clear and reiterate again, that does not include face coverings, face masks and surgical masks. These are not considered respiratory protective equipment. They are considered personal protective equipment in the surgical mask realm, but they aren't actually respiratory protective equipment. When I'm talking about respirators and RPE, I'm talking about respirators that are mandated by Australian Standard 1716. And this specifies performance and testing criteria for respirators. And it's relevant to the particulate filter respirators and air purifying respirators that we use in the setting of infectious aerosols. Surgical masks, on the other hand, as I said, they are considered a medical device and they're mandated by Australian Standard 4381. And they have certain performance criteria around fluid barrier protections and permeability standards, but filtration efficiency is not a criteria because they aren't considered respiratory devices. So talking about those that are considered respirators and respiratory protective equipment, as I said, the effectiveness of those is really dependent on how they're used. So Australian Standard 1715 mandates or provides guidance on how we can make sure we get the highest level of protection out of that respiratory protective equipment. So it says that we need to have a respiratory protection program and use our respirators as part of an overarching program. So it's not good enough for an employer to grab respirators, hand it to the employees and say, off you go. There's a whole lot of roles and responsibilities about managing a respiratory protection program. There needs to be a qualified, experienced administrator, and it provides guidance on the correct selection of respirators for purpose, education and training, fit testing, issuing, maintenance, and all of those things that go into a comprehensive respiratory protection program. In terms of healthcare, which is obviously a really major workplace when it comes to the hazards associated with COVID-19, South Australia have had a respiratory protection guideline since about 2013, which was updated last year in the context of the SARS-CoV-2 pandemic. New South Wales and Victoria also have respiratory protection programs now in place. Both of them were developed last year, 2020, and they obviously have varying opinions and commitments to things like fit testing and respiratory protection, but they have guidelines now, which is really important when we're looking at the effectiveness of respiratory protection. Kate touched on this a little bit earlier in terms of the selection of controls, and certainly respiratory protection is no different. So when we're selecting, as occupational hygienists, we're very familiar with selecting our respiratory protection based on the contaminants that we're dealing with. So whether it's in the form of a particulate like dust fibres, mists or fumes, or whether it's as a gas or a vapour, will depend on the type of respiratory protection, the nature of the substance, and then we often do measurements around exposure and we compare those to exposure standards, and that helps us determine which sort of respirator we need and what is the protection factor that we require. Now, obviously with SARS-CoV-2, this is a microorganism. We don't have any occupational exposure standards. We don't know, any sort of safe levels of exposure. So it makes selecting the type of respiratory protection a little different, but the principles are much the same. We need to understand whether the organism is pathogenic to humans, if it's hazardous in the workplace, how it's transmitted, and if it is transmitted into the community, the effects of that, and do we have effective treatments for prophylaxis for the hazardous organism. And obviously, when it comes to SARS-CoV-2, we understand that it's as Kate pointed out, it's a virus, and those virus particles are transmitted in aerosols. So these are particulates. And if you have a look at the Australian Standard, it provides some guidance on classifying infectious aerosols and infectious agents or microorganisms in terms of their risk category. And I'll let you read the detail, but essentially SARS-CoV-2 is considered a risk group 3, which says that if we want to protect workers from airborne exposure to this microorganism, then we're looking at respiratory protective equipment with a P2 filter. Now, I've mentioned P2 a couple of times, and just to reiterate for those that may not be familiar, the P stands for particulate. So we're talking about particles and droplets, aerosols in the air, and so we need a particulated filter. The Australian Standard talks about a P2, and then the terminology has been quite interchangeable throughout this whole pandemic in terms of an N95 respirator. And just to sort of provide some clarity, a P2 respirator has roughly around 95% filter efficiency, and N95 is the American version of the same thing. That's their classification system. and other countries have different classification systems. And probably the other most common one we come across here is the KN95, which is the Chinese classification system. Now, the reason we've become more familiar with these things over time is because with the pandemic came a huge demand for respiratory protection and respirators. And we've seen a lot of respirators that are manufactured overseas and that are rated according to international rating systems coming into Australia. So it's good to understand what they are, but unfortunately there's also been a real influx of counterfeit and non-standard respiratory protection coming into the country. And I don't want to talk in detail on this, but just point to this absolutely fantastic document that was produced by the AIOH in collaboration with a whole lot of organisations around, determining that your respirator you're purchasing is actually of adequate quality and it meets the standards required and isn't a substandard or I guess a counterfeit type respiratory protection. So when it comes to respiratory protection, Kate's talked about the size of aerosols and that though the particle size can vary greatly from upwards, 50 microns down to, 1 micron in size. And so when we're talking about respiratory protection, we're talking about filtering that air before we breathe it in. It's really important that all the air we're breathing in is going through the filtration on that respirator and cleaning the air before we inhale it. So I've just got a little demographic here. If we're wearing a tight fitting respirator, so a respirator that fits to our face and seals to our face, then when we breathe in, all the air we breathe in will be dragged in through that filter. It'll be filtered and the air that was actually getting into our respiratory system will not contain those hazardous particles. If we don't have a good seal of our respirator, obviously air will move through the path of least resistance, and certainly moving in air is much easier than moving through a filtration media. So if we're breathing in and there's no seal or there's gaps in the seal around this respirator, then particles are going to get in around the side of the respirator and get into your breathing zone, and they're not going to go through the filter and will end up with contaminated air in the breathing zone. So basically, if we don't have a seal, we get leakage and we have potential exposure to those hazardous particles. Now, obviously, we are of all sorts of shapes and sizes, and that includes our face. So when we're talking about respiratory protection being reliant on achieving a really good seal to our face, what might seal my face is going to be very different to what might seal your face. And we have a huge range of face shapes in society, and respiratory protection is not a one size fits all. So while we use some general rules to select the type of respiratory protection, it's particulate rated, it's N95, it actually determining which specific P2 respirator will actually fit your face is something that needs to be considered, because not everybody will get the same level of protection from the same respirator. So the way we achieve this and the way we can determine, how, if we're getting a good fit, and it's a legal requirement for organisations if they're providing personal protective equipment to ensure that it is of a suitable size, fit and comfort. And the way we achieve that with respiratory protection is to carry out respirator fit testing. And this is, once again, guidelines for this are provided in the Australian standard. And it's really about checking that a tight-fitting face piece respirator matches the facial features of the person wearing it and provides an adequate seal to ensure all of that breathed air is dragged through the filter and you're getting an appropriate level of protection. There's a couple of different methods for fit testing. There is a qualitative fit test method and a quantitative fit test method. I won't go into detail in the interest of time, but they do essentially have pros and cons, and some are suitable for certain sorts of respirators and some are not. However, both of these methods are supported in the Australian standard. They're both valid methods of fit testing. So who needs to be fit tested? Anyone who uses a tight-fitting respirator must be fit tested before they use it for the first time. And you may need to be fit tested on several types of respirators, styles and sizes before you find one that gives you an adequate level of protection or an adequate fit. You need to be fit tested for your respirator before use for the first time. And if you're using a different sort of respirator, then you need to be fit tested for that one too. So whatever you're fit tested with is one that you need to wear in the workplace, because we know that that one can achieve an adequate seal if donned correctly. It needs to be repeated annually, your fit test, and also if there's any significant changes in your physical features. So weight loss or weight gains is a particularly common reason for the fit of a respirator to change. So the fit testing not only confirms that you can achieve a satisfactory seal, but it confirms that it's comfortable for you and that you can actually wear it in the workplace and perform the duties that are required of you. The other thing that fit testing provides is an opportunity to have one-on-one training with the wearer on how to actually don the respirator correctly, how to do their seal checks, making sure it's fitting correctly when they're out in the workplace. And it helps meet those legal requirements around a suitable size, fit and comfort of the PPE that's provided. So just briefly, I'd like to introduce, for those who may not have heard of it, the Respirator Fit Testing Training and Accreditation Program. This is an initiative of the AIOH, and it's a national fit testing training and accreditation program that is aimed at improving worker health protection for those wearing tight-fitting respirators by ensuring that fit testing is carried out in by competent fit tested to the required standards. So ResFit provides a standardised training syllabus. It provides a pathway for competence for fit testers to sit through a theory and a practical exam. And it also provides some really valuable resources for workplaces in terms of the sorts of respiratory protection, fit testing protocols, and resources around accessing trainers, accredited fit testers, and some other really good documents. This is just an example of the Find the Fit Tester page. It's just one of the things that you can find on ResFit, but there is some really good resources up under that resources tab too. So very quickly, you may have heard of the term fit check. And just for clarity, to ensure that you understand the difference between a fit test and a fit check, unfortunately, these terms have been used interchangeable and they're not the same thing. So I've mentioned that a fit test is about selecting a respirator that is suitable to your face shape and that is capable of achieving a good seal and providing a minimum level of protection. A fit check, or otherwise known as a user seal check, however, is something that as a wearer of respiratory protection, you should do every time you don that respirator. So the fit check is about ensuring that you've put the respirator on correctly, you've adjusted it, there's no folds, there's no leakage, you put it on, you do either a negative or a positive user seal check, and it tests that you have it on and it's fitted correctly and it's providing you with the level of protection that you think it is. A fit check is not a substitute for a fit test. It is something that's done in addition to a fit test every time a respirator is donned. One of the things that does, I talked about having it adjusted correctly and donned correctly to get the optimal protection, and I really can't talk about respirators without mentioning facial hair. We're talking here about negative pressure, tight fitting respirators and the importance of a seal between the face and the respirator. And one of the major factors that impacts on that seal is the presence of facial hair. So Kate once again talked about the size and the very small size of some of the aerosols that are generated that contain infectious particles. When we look at that in comparison with the size of human hair, the human hair is significantly larger. And if we had a human hair sitting between our respirator seal and our face, then we will get small air gaps around the edges, and that provides a pathway for infectious particles to get into our breathing zone and for the respirator to leak. So any sort of facial hair can have significant impact on the level of protection provided by respiratory protection. So it's really important that for negative pressure respirators, tight fitting respirators, people are clean shaven. So that just, basically those things I've just talked about reiterate the reason why respiratory protection is the lowest rung on the hierarchy of control, because there's so many factors that could actually impact on the effectiveness. And that once again really reiterates the importance of training the user in the use of the respiratory protection. So yes, we need to select it correctly for the hazard that we are dealing with. We need to fit test it and make sure we're providing the appropriate respiratory protection to the wearer, but they also need to be trained in donning it correctly. So I'm sure many of you have seen people walking around with a respirator and the nose piece sitting quite firmly and securely under their chin. Very common to see out and about in public. People need to understand how to don their respirator correctly. They need to understand how to do a user seal check to ensure that they've donned it correctly. They need to understand the impact of wearing other head-borne PPE with it, and they need to understand how to maintain it and care for it. And that's particularly important in reusable respirators. You know, respirators themselves can become a fomite and become a pathway for transmission if they're contaminated and if they're not maintained, cleaned and cared for appropriately. And certainly when it becomes, you know, when we're talking about disposable respirators, it's about actually disposing of them after use. There's also some adverse effects from the prolonged use of PPE. There's been a lot of reports of chafing, skin effects, acne, dermatitis, you know, fatigue, headaches, those sorts of things from using PPE for long periods of time. And so people need to understand what precautions to take to mitigate those risks. And the other thing people need to understand is the limitations of the respirator that they're wearing. So they need to understand all of these things that impact on the protection provided by their respirator. So, you know, really respirators can work, but they only work if they're used correctly. So in summary, to sort of just summarise what we've spoken about today, myself and Kate, we've introduced the chain of infection as a pathway for transmission of infectious, you know, airborne transmission of COVID-19 or SARS-CoV-2. You know, we've talked a bit about source control and controlling the amount of aerosols in the air. We've talked about, you know, ventilation and controlling the pathway of those infectious particles. And then we've talked about protecting the host with respiratory protection. So, and looking at those things through the eye of the hierarchy of control. And as Kate mentioned, in terms of, you know, hierarchy of control for source transmission, there's certainly a lot of other things besides face masks. And certainly in terms of, you know, receptor transmission, there's other things available besides PPE. But in our current environment, those are the two sort of most highly relied on things. So it's important that we get them right. So essentially, you know, when considering programs for the control of airborne transmission of COVID-19, it's important that you consider the application of the hierarchy of control. It's important that you understand the chain of infection, but it's also really important to understand that every single workplace is different and that you will need to do a risk assessment of the particular aspects of your workplace, what the risks and associated hazards are, and get some expert input into developing, you know, appropriate control programs based on the hierarchy of control. So I think that I will leave it there. And I know that there's been some questions in the question and answer. And certainly I'm happy to take the first one around masks with exhalation valves. So Christian has, just to read it out to you, has said that he's noticed an Australian television news that some members of the public wear respirators or masks with exhalation valves to protect themselves against COVID-19. If the wearer has COVID-19, the exhaled air will pass directly out of the mask through the valve without being filtered. Shouldn't the government guidelines on face masks be more specific? So I just, absolutely. So that's one of the issues with, you know, that's one of the factors of confusion is, you know, the purpose of face masks versus the purpose of respirators. So face masks for the public as a public health initiative are absolutely about protecting and stopping people from transmitting the virus from themselves to others. They aren't designed as, you know, a protection from respiratory transmission of aerosols out in the public. So that's, in that context, absolutely, face masks with valves are going to, you know, definitely not serve the purpose. Whereas in a workplace, when we're talking about protecting the receptor and the worker, then obviously valved or non-valved is not as much of a consideration unless that worker is potentially infected. And then obviously if they have a valve, they also have the capability of transmitting it.
Okay, well, I can't thank you guys enough for that fantastic presentation. I'm sure it was an awful lot of information that might have been day-to-day bread for some people, but obviously new and informative for other people. And what I love about it is the crossover between our two professions. The hierarchy of control, biocontainment, and negative pressure is all part of the biosafety and biosecurity Bibles too. So there's a lot in common, there really is. But it was a far more informative session than I'm sure a lot of biosafety advisors were used to when it comes to occupational hygiene. I hope we can do the same for you one day too. So what I'm going to do now is, Julie's already answered one of the questions, but Kate's been typing away feverishly answering a lot of the questions, which a lot of the participants might not be able to see the answers for. I'm not sure if that's true, but what I'm going to do is read out the questions and the answer that Kate has typed up so that you're all aware, just in case it was something you were thinking about too. So from Hayden in Perth, he has asked a question about if we are bringing in more air from the outside, i.e. more ventilation, what happens when you have a highly contaminated HVAC system or a wall mount split system recycling the air as in aged care or a ceiling cassette? Hospitals have highly contaminated HVAC systems, including the ductwork. Kate has answered, a wall-mounted split system that recirculates the air may transfer the virus through airflows between people. I don't know if you want to expand on that anymore, Kate?
Yeah, so I guess that the challenge is, and this goes back to the section of my presentation where I'm talking about understanding airflow, and it's an incredibly complex system. So we would recommend against recirculating airflow because it's just building up those aerosols in that particular space. And if you think about the aged care outbreaks that we've had and the low level of focus on improving indoor air quality, I don't think it's a surprise that those two are somewhat connected. When you do go into a system and there's just recycling of air, you should expect that those aerosols are building up inside that space to some extent, and that will depend on the type of filtration system in those units, in addition to how well that filtration system is maintained, and does it actually work as per the plans per se? Is it operating as per design? Obviously, we look at trying to get and maximise the amount of fresh air and minimise recirculation. But in many situations, that is at, I guess, loggerheads with other aspects of ventilation, which is around sort of maintaining comfort and sustainable energy practices as well. And so there's always an element of recirculation that's typically designed into a system. The challenge here is that we want to minimize that, and typically that would normally be maximized. So we're at two ends of the spectrum.
Okay, so another question from an anonymous attendee. Is COVID-19 virus only a respirable issue, or can it be absorbed through other pathways? Kate's answer was that the modes of transmission include airborne, droplet, and formite transmission. Again, do you want to expand on it, Kate, or something?
Look, I will say I personally am not aware of it being transmitted through any other pathways. But like everything with COVID-19, what you know about today and what you learn in 6 months' time aren't always exactly the same. So my mind remains open. But to be honest, primary concern in terms of minimizing risk of transmission is around the elimination of the pathway of airborne, droplet, and foamite transmission. So that's where we're really focusing.
Yeah, and yeah. As a virologist, I would totally agree with that.
Yeah, there is also some talk around, I mean, obviously mucous membranes and the eye as well has been proposed as another source or another pathway of entry.
Yeah, there is a lot of research going through the eye. But yes, but predominantly it is airborne air particles, absolutely. Now this is a good one, and I didn't realize this was happening. What's your stance on the CDC endorsed use of surgical tape on exhalation valves to modify P2, negatively pressured close-fitting respirators, to make it comparable to a non-valved unit? Sorry. And what is your opinion of exhalation valves on the P2N95 respirators being equally effective for source control as surgical or homemade face covering? Would you make a hypothetical recommendation to our workplace that it's okay to wear a valved P2N95?
So I tried to answer this from one perspective, picking up on a NIOSH study, and like everything, like I mentioned before, what our knowledge is today may not be our knowledge in 6 months. But a study that was done by NIOSH in the States looked at exhalation of aerosols coming out of surgical masks versus N95, which is the equivalent of our P2 respirators, and the exhalation valve, and I think found no real significant difference. But I think the question is around, should you stop or retrofit something to change your mask to modify it? And our general recommendation as occupational hygienists is that you shouldn't be fiddling with any type of personal protective equipment outside the manufacturer's instructions at any point in time. And the second section of the question was, would you make a hypothetical recommendation that it's okay to wear a valved P2N95 or a surgical homemade face covering? Again, it goes back to what is it that you're seeking to achieve in a workplace where you need to protect workers from airborne transmission of COVID-19. It would absolutely be respiratory protection and not a surgical or a homemade face covering. And early on in the pandemic, it was really difficult to get non-valved respiratory protection because in industry, that's typically what we use the most of for other airborne contaminants. But now I think the supply chain has, I guess, caught up, and now we see a lot more respiratory protection that is non-valved. I don't know, Julia, if you want to add anything to that.
Yeah, you're absolutely right, Kate. And so certainly early on, there was, and even now, if there isn't if there is a supply issue, they are saying you can wear a valved P2 with a surgical mask over the top of it if you are working in those high risk areas. But once again, it does come back to what's the intent and purpose of the mask that you're wearing. Is it source control? Is it about stopping you from transmitting it to other people? Or is it actually about worker health protection and protecting the worker in that environment? So, P2 respiratory protection is absolutely a must when you're protecting the worker. If you also are wanting that to act as source control, then, there's evidence that a P2 with an exhalation valve is equally as effective as a surgical mask. But is a P2 with an exhalation valve equally as effective as a P2 without an exhalation valve? Well, possibly not. But it's really about what we really, that's the whole point of this talk, is about assessing the situation you're in and what you're trying to achieve from either your respirator or your face covering or your face mask.
Okay, one of the open questions now, which you probably haven't had a chance to look at, ladies. If you had a choice only between fresh air and ventilation or negative airflow, is one better than another, or is this more complex and dependent on the situation?
Oh, okay. First answer is it's very complex and dependent on the situation, because negative airflow is going to draw air in, so hopefully that's drawing in fresh air, because if I have negative airflow and it's drawing in contaminated air, I definitely don't want that option.
There's also a lot of questions about why the governments haven't been concentrating on aerosol transmission and really concentrating on surface sanitisation. And a lot of questions about security guards and other staff in hotel quarantine continuing to be provided with surgical masks. And they're wondering if you or the profession have been contacted to give advice on this.
So I can attempt to answer it. I think you'd have to ask the government bodies as to why they haven't focused on airborne transmission. But from an outsider looking in, I think it just relates to the types of experts that were initially engaged, and now we've seen more diversity of expertise being engaged by government departments to have a greater understanding of, I guess, infection risk between people in high-risk settings and other professions, in addition to occupational hygienists like aerosol scientists, aerosol physicists, mechanical engineers, ventilation engineers, etc. And so with that increased level of diversity of expertise, you're going to get a more broader understanding of airborne transmission. It is incredibly disappointing to see high-risk workers still in July 2020, such as security guards, being provided with surgical masks, because we know that they're source control and they're not respiratory protection. And I firmly believe that every worker has the right to a safe working environment, and by simply going to work shouldn't be putting their own health or the health of the communities around them at risk. And unfortunately, we have seen quite a disparate response to hotel quarantine, or the controls in hotel quarantine, across the different states. Some states are way ahead of the others, and some states are just catching up. And I won't mention which ones are which, but you can probably Google the hotel quarantine manuals in the different states and find those answers out pretty easily yourself from a bit of Googling, if you have a look at ventilation requirements and respiratory protection. And the last section of your question, have we been engaged? So there's lots of occupational hygienists that have been engaged in hotel quarantine to support state governments' responses. I'm personally not one of them, but they are actually very amazing, highly technical experts that have really brought hotel quarantine control to the levels that they need to be. So we're very grateful that their expertise is being engaged. Myself and some others are also on state and federal task forces to help with the state and federal government's response to COVID-19. But I'm not aware of specific hygienists being involved in hotel quarantine planning per se, but I can't speak for all thousands of occupational hygienists across the country, so I hope they are.
Okay, well, unfortunately, we're out of time.
Sorry, June, could I just answer one question, because I think it's quite important. Just very quickly, someone's asked, why do businesses go for deep clean if the only method of transmission is airborne? So just to clarify, airborne is not the only method of transmission, but when we were talking about the respiratory tract, the respiratory tract is the portal of entry into the body and mucous membranes of the eye. But, you know, transmission is either by airborne or droplet or fomite contact. So that's why deep clean is important. So just to clarify that we were not saying that airborne is the only method of transmission, but clearly it is a method, and it's in certain situations a significant method of transmission and needs to not be discounted.
Yeah, and we all touch our faces every single day in life.
Yeah.
So with that answer, I'm going to wrap up this webinar. I'd like to thank Kate and Julia again for their expertise, knowledge, and their commitment to doing this for ABSANZ. As I said before, I hope we have many more collaborative events, and I'm sure ABSANZ will be able to do the same for you one day as well. So for all of those online, thank you for attending today. I hope you got a lot of information out of it. And I wish you all a healthy and safe time. Thank you and goodbye.